Hey everybody, in today's video, we're gonna at least introduce transformations to achieve linearity. And I just kind of have the outline plotted for us here. If we're given a set of data that is curved and very distinctly nonlinear, we can do some transformations to make the data form a linear relationship. And so it really just boils down to what we're trying to be able to do is apply linear regression to nonlinear associations. Everything that we've done so far has been roughly linear, and that's why we've been able to do linear regression. So hey, a couple different ways you can do this is just so applying transformations would be, I don't know, like maybe taking the log of the variables. If this looks like a logarithmic function, it increases rather quickly, kind of levels off here, and then really flattens out. So we can take the log of one or both variables, maybe do the square root of x or something. I'll walk you through an example where we transform a curve into something linear. So let me pull up the data that I've got um, regarding oil spills. Let's go here. All right, so hey, in this data, kind of the situation that's going on here is a company can take aerial photographs of an oil spill and determine how much oil is actually in the lake or the ocean or whatever, just by measuring the radius of the oil spill. So we've got some data here that they've tested inside of a lab. So by when the oil spill has a radius of 1.8 meters, the volume in milliliters of the oil spill is 10, and that's plotted right here. Now, this isn't a perfect example because it doesn't appear that curved, and it certainly is pretty strong, but still, it does. It follows a little bit of a curved pattern. If I was to make a residual plot, you would definitely see a pattern where we start where we're uh, under predicting the actual values. We start to dip below it, as you can see right here, and then our predictions start to increase again. Or we start to under predict right here. So there was a pattern, and we can transform this. And so kind of the idea here is, well, hey, the radius, that's in a one-dimensional unit. The radius is just length, whereas volume is a three-dimensional unit. Like traditionally for volume of like a cube, you would do length times width times height. And the radius would just be essentially a length. Um, so to transform this data to make it even more linear, what I did was square the radius. The height remains pretty constant in this oil spill. The oil is not really going to like sink down to the bottom of the ocean. It's just going to be pooling right on top, and then like the ocean way down here. Terrible drawing. I'm just going to go ahead and erase that. Hey, so what I did though to kind of match the units a little better is square the radius and then replotted the data. So let's look at what that looks like. Again, I just took the radius and squared it. So here's my transform data. So that 1.8 squared gave me, again, I just went to that sheet and squared it, and it gave me 3.24. Now, if you look at this plot, you should notice that it is much more linear, very strong relationship. And I just did that by essentially trying to match the units. Volume is a cubic unit, radius was just length. So by squaring the radius, I've gotten it closer to being linear. Certainly a very strong relationship at this point. So what we're going to do today is really just focus on reading the computer output whenever a transformation has taken place and come up with a regression line equation, and then use that regression equation to make a prediction. So I got the computer output for this data, the transform data right here. So here's our regression analysis, volume versus radius squared. Not just the radius, the transformed radius. So we've got the y-intercepts, we've got radius squared as our explanatory variable, and it gives us some other statistics down here. Remember, we don't really need to worry about these three columns at this point in the class, and then we never have to worry about the adjusted r squared. Anyhow, write the equation of the least squared regression line and define the variables used. So when your question asks you to define the variables used, instead of using y hat, you'll actually use the response variable. So we are trying to predict the volume of the oil spill. So for our least squared regression line, it's going to look like this. The predicted volume is equal to. So it's really just follow the same format as our simple linear regression for relationships that were already linear. I've got this y-intercept, negative 0.852, 0.852, plus the slope, the coefficient right here, right? The coefficient of our explanatory variable is going to be 3.2106 times. So this is where it kind of changes. We're not just having a linear variable there anymore. We've got the radius, but we've got the radius squared. We squared the radius to make this regression analysis. So hey, that's going to be used in our least square regression line. Okay, so part 2 here is use the regression line created to predict the volume of oil from a spill with a radius of 2.9 meters. Very easy then, we're just trying to predict volume. So the predicted volume is going to be equal to negative 0.852 plus 3.2106 times 2.9. And then remember, I am squaring this radius. So I'm going to put a square there. And this will just be a job for the calculator. Let me get one out and do it real quick. Make sure that we're all on the same page with our solution. So I've got negative 0.852 plus 3.2106 times 2.9. And that is going to be squared. Okay, so it looks like I get about 26.15 for our volume. 26.15 milliliters was the unit that they were using. So that's it. Again, what I want to focus on today is look at the regression analysis for transformed variables and try to come up with the equation. Really just what happened to our variables? How did they transform the variables? They could have taken the square root of volume to transform the data to where you would have just went, well, the square root of our predicted values equal to all this stuff. It'll tell you in this regression analysis too what happened to the variables. So pay close attention to those. Try to come up with the regression equations, make predictions using those equations. And then in the next class period, I'll give you some hints on how to actually do the transformations when you're given a curved pattern. There's a lot of different methods to do, like I just squared the one variable. Maybe we could have taken the log of both sides or something. So again, I'll discuss that in the next video, how to actually go about transforming the data. And that's going to do it for this video. So hey, thanks for watching. See you in class. Bye-bye.